Okay, so we'll move on to question number 4. This is in exercise 2A in M3. Exercise 2A, question number 4. Okay, so they say a light elastic spring of natural length A and modulus of elasticity lambda has one end fixed. A scale pan of mass capital M is attached to its other end and hangs in equilibrium. Okay, the first thing is in question number 4. So they say there's a light elastic spring of natural length A and they are fixing onto the other end, they are fixing a scale pan of mass M. So when you fix the scale pan of mass M, what do you expect? Definitely it will be because of the weight of the scale pan, the string will extend slightly, right? So there will be an extension. This is the beyond its natural length. So you have the scale pan here. Okay, so you have attached the scale pan. Okay, so because of the weight of the scale pan, you will have some kind of an extension. So natural length of the elastic spring is A. Okay, natural length of the elastic spring. So this is the natural length. And let's say this is the extension because of the weight. Because of the weight of the spring, this is the extension. Okay. So they are asking you a mass simple M is gently placed in the scale pan. Okay. So when it is in this state, they are again placing on top of this. They are placing a weight simple M on top of this. So then what happens? You expect this to go further down, right? Because of the weight. So they are asking you find the distance of the new equilibrium position below the old one. Okay, you have to find the distance of the new equilibrium position below the old one. So what do you mean by new equilibrium position below the old one? Old equilibrium position is this one, isn't it? So I will name this extension as x1. Okay. So in this case, I will first find x1 before we go to add the mass simple M. First, let's find this extension. Okay, how do we do this? So let's mark all the weights. What do we have here? We have the weight of the scale pan, capital MG, and we have the tension, right? So obviously, what are the forces here? The weight of the scale pan and the tension. So I will say this is tension 1 because it's the first system. So then let's make it equal. We know the system is in equilibrium. So tension 1 must be equal to mg. So tension in an elastic string or spring, we can find it by using Hooke's law. What is it? Tension is equal to lambda x over L, right? So tension equation is lambda x over L. Lambda x over L. So lambda is the modulus of elasticity. Extension is x1 here over natural length in this case is A equals capital Mg. Are you guys with me? Lambda value is given in terms of lambda. They have given you here the modulus of elasticity is lambda. It's given as lambda. So we'll keep lambda as it is. Shall we find x1? So x1 is mga over lambda. Do you agree? x1 is mga over lambda. This distance. This distance is mga over lambda. There are no figures here. You have to do it completely with letters. Sum. That's the difference in this particular sum. Okay, so now I found the first equilibrium position with the weight of the scale pan. Now they say there a mass of simple M is gently placed on the scale pan. So you keep another mass M simple M here. So what do you expect when you keep another weight? What do you expect when you keep another weight? This will further stretch. It will further extend. So it will further extend. So you have two weights here. Right, so now there are two weights here. You have the weight of the scale pan, and you have the weight of the scale pan, and you have the weight of the weight. They have kept here mass simple M. So you have simple mg and capital Mg, weight of the new mass and the scale pan. So then, does the natural length change regardless of what weight we use here? Natural length is a constant figure. So this is still A. Natural length of the string is A. Okay, and then let's say the new extension is x2. Okay, so basically they are asking you to find what? Find the distance of the new equilibrium position below the old one. So this is the old equilibrium position, right? This is the previous equilibrium. Equilibrium position is actually the question is, you might be thinking, what is equilibrium position? Equilibrium position is where it is at rest. Now when you place this weight here, it's at rest, right? It goes a little bit distance downward and it stays at rest. That is the equilibrium position. Over here, this was the equilibrium position. with the scale pan, it extended a little bit. Now it's in rest here. So this is the first equilibrium position. When you place the mass, simple M, it goes further down. And then it's again at rest in another place. So this is the new equilibrium position. They are asking you to find the distance between the two equilibrium positions, which means what? They ask you to find this distance. They are asking you to find this distance. Basically, question is to find what? Find x2 minus x1. That's what you got to do here. You have to get the difference between x2 and x1. Are you with me? The difference between the two equilibrium positions will give you the distance of the new equilibrium position below the old one. Are you with me? This is the first equilibrium position. And this is the second equilibrium position. Equilibrium position means it's at rest there, it's not moving. Okay. Right, so let's go for the tension here. What are the weight, the forces we have? Obviously, now again we have a tension here, right? So tension, I'll say it's tension 2. So what do we say here? The tension 2 value is equal to? The tension 2 value is equal to capital Mg plus simple mg. Okay, the tension 2 value is equal to capital Mg plus simple mg. Okay, so tension 2 is again, tension is always lambda x over L. That is the main equation in this lesson. So what is the lambda value? Lambda is unknown. That's lambda. X is x2, right? The extension, because x is always the distance that the string has stretched beyond its natural length. So natural length A, this entire distance is the extension. I have taken it as x2. So lambda x over natural length is, natural length will not change. Natural length is A equals capital Mg plus simple mg. So I end up getting here x2 equals capital Mg plus simple mg into A over lambda. Guys, do you agree with me? I could, separate this as capital Mg A over lambda plus simple mg A over lambda. Guys, do you agree? Okay, so they're asking us to find the distance of the new equilibrium position below the old one. So the distance that they require, the distance they want us to find is the x2 minus x1 distance. So x2 distance is capital Mg A over lambda minus simple mg over, plus simple mg A over lambda. You have to subtract this with capital Mg A over lambda. The capital Mg A over lambda cancels out. Can you see? The distance of the new equilibrium position below the old one is simple mg A over lambda. So this is the distance of the new equilibrium position below the old one. Okay, I hope this is clear with you all. Okay, so next I'll move on to question number 5. They say an elastic string has length A1 when supporting a mass M1 and length A2 when supporting a mass M2. Find the natural length and modulus of elasticity of the string. So basically over here, it's given to you, everything is given to you in terms of symbols, right? So you'll have to get your answer probably in terms of M1, M2, A1 and A2. So let's just draw a diagram. They have not mentioned us which mass is higher. So we'll, let's see how it goes. There's an elastic string of natural length A1. So basically I'm going to draw it with the mass. Okay, so when you are placing the mass, the string will extend. So this is the natural length A1. Natural length is not A1. They say here what? Natural length is what we are supposed to find. An elastic string has length A1. Length A1 means what? The full length of the string is A1. Right? The full length of the string is A1. So this full length is A1. Let's say the natural length is L. Natural length is what we are supposed to find. Natural length is L. So I will say the mass of the first one is M1. So weight will be M1G, right? Weight is mg. So because the mass is M1, weight will be M1G. Tension, let's put it as T1. Okay, so what we'll do is first let's write the equation. I think we'll have to go for a pair of simultaneous equations here to get natural length and the elasticity. Okay, so shall we write the equation for the first case? So over here, the tension balances out with the weight. So that's why it will be in equilibrium. So tension 1 equals M1G. So tension is lambda x over L, isn't it? Tension is lambda x over L. Okay, so tension is lambda is unknown. Extension. How do we write the extension here? The entire length of the string is A1. Natural length is L, which means the extension, instead of working with X, we can write the extension in terms of A and L, right? Because I'm supposed to find L here. So the extension should be what? The extension should be A1 minus L. Do you agree with me? The extension, the length that the string is stretched beyond its natural length, should be A1 minus L. Do you agree? So lambda x over natural length is L equals M1G. Let's simplify this slightly. Lambda A1 minus L equals to M1G. Let's leave it like this. Shall we go for the other equation? In the other equation, they say what? When the string has an elastic string has length A1 when supporting a mass M1 and length A2 when supporting a mass M2. So again, if you go with the weight A2, the weight M2, I think you can see it's the exact same scenario. Okay, it's the exact same scenario, just that the length is now different. Natural length will not change regardless of what weight you apply to the string. The natural length will not change. The entire length changes because the extension depending on the weight will change. So this is the new length A2. The new tension, I'll say it as T2. Okay. Yeah, sorry, over here I have to take the L, right? So M1G, this L, when it goes here, I've forgotten that. Yeah, M1GL. Okay. So we'll continue over here, right? So over here, let's again write the equation for the equilibrium. Tension 2 equals M2G. So again, tension 2 is lambda x over L. Lambda, what is the extension? Extension is how much the string has stretched beyond its natural length. So that will be A2 minus L, isn't it? A2 minus L over natural length is L equals M2G. So we can again do the same thing. Lambda A2 minus L equals M2GL because we move the L to the other side. So you can see I have two equations. And one of the easiest ways of getting through these two equations is what? One of the easiest ways to get through these. Now the thing is I have to solve these two equations simultaneously and get the unknown value of lambda and L. Remember your answer is supposed to come in terms of M1, G1, M1, M2, A1, A2. So M1, M2, A1, A2 are supposed to be part of the sum. So you're supposed to find the lambda and L. So actually this is what? A pair of simultaneous equation, because you can see there are two unknowns, just the lambda and the L. Okay, that's just lambda and L. So the easiest way to do this would be what? You can simply what? Easiest way to get through this is to divide. Divide the two equations because many of the things that are unnecessary can cancel out. So when you divide the two equations, what do we get? First equation, divide by 2. Let's divide lambda A1 minus L over lambda A2 minus L equals, what do we get on the other side? M1GL over M2GL. So you can see now many terms cancel out. What are the terms that cancels out? Lambda cancels out. G and L cancels out. Can you see? A1 minus L over A2 minus L equals M1 over M2. Let's cross multiply and do what? Make L the subject. So you can see you get L in terms of M1, M2, A1, A2. Okay, so I get here A1, M2 minus L times M2 equals M1, A2 minus M1, L. Okay, so take all the terms with L to one side. So depending, you can choose it to any side you want. Okay, so you can take it to any side you want. I'll take this over here. It can't be any side. Okay, if you want, you could take the LM2 to the other side. So I get here L M1L minus LM2, or you can say M2L. Okay, I think M2L is preferable. M2L, it doesn't make a difference. Equals, I'll take the A1, M2 to the other side because I want to keep the L terms in one side and everyone else that doesn't have L on the other side. So over here I get M1A2 and here I get A1M2 minus A1M2 or M2A1. A1M2 and M2A1 are exactly the same. Great. So I can take L out and I get M1 minus M2, M1A2 minus M2A1. So L equals M1A2 minus M2A1 over M1 minus M2. So this is the natural length. Agreed? So now it's time to substitute the L value. The question says us to find the natural length and the modulus of elasticity. Remember the natural length, this letter L is something that we input. It was not a part of the sum. So when you're trying to find your lambda now, next you're trying to find lambda. When you try to find lambda, remember your answer needs to be in terms of A1, A2, M1, M2. It cannot be in terms of L because L is a value that we use. Okay, so we came up with the letter L for the natural length. So let's substitute, right? Substitute. Shall we put it to equation 1? So lambda into A1 minus L equals M1 GL. Okay, so there are two places to substitute L. Can you see? I have replaced L in two places. Let's do it. So lambda times A1 minus, okay, L is gonna be M1 A2 minus M2 A1 over M1 minus M2. Better to put it inside a bracket. Equals M1GL, right? Again, there's M1GL, which means this L also should be substituted, which is M1A2 minus M2A1 divided by L. So just do this really, really slowly and carefully. Your simplification needs to be correct. Sorry, what did I do here? M1A2 minus M2A1 divided by M1 minus M2. Right? Okay. Shall we simplify? So I think over in this side, it's better that we go for the common denominator. Shall we go for the common denominator? What do I get here when I go for the common denominator? So M1 minus M2 will be the common denominator. And this multiplies M1, A1. The A1 multiplies with M1 and minus M2, A2. M1, A1 minus M2, A2. This one, this bracket, you have already the M1 minus M2 denominator is there. So there's nothing to fix here. This bracket must be open with a negative sign. When you open with a negative sign, so minus M1A2 and this will be minus minus a plus M2A1, right? So this is going to be minus M1A2 plus, this is going to be plus M2A1 equals M1G times M1A2 minus M2A1 divided by M1 minus M2. So do we have like terms? Do things cancel out? M1, A1. Okay, so I get this big term here, isn't it? Okay. I think I can cancel out on both the sides. Do you guys see that M1 minus M2 is a denominator on both sides? So I can cancel out this entire denominator. Do you agree? Okay, and then I think there's one more thing that I've done here, right? M1, A1, so just be really cautious, minus This is M2A1, right? M1A1 minus M2 times A1. Can you guys see? So over here, I've done a small error, right? So this should be fixed. M2, this is not M2A2, this is M2A1. Can you guys see? Because M1A1 minus M2A1. Then I think we can see one term clearly cancels out. Can you see? M2A1, M2A1 will clearly cancel out. Agreed? Because there's a minus M2A1 and there's a plus M2A1. So I get here lambda times M1A1 minus M1A2. On the other side, I have M1G times M1A2 minus M2A1. Okay, so be cautious here. Over here, I can take M1 out from this equation. When I take M1 out, I get lambda M1 times A1 minus A2. Here, M1G times M1A2 minus M2A1. Shall we make lambda the subject now? So M1G times M1A2 minus M2A1 divide by M1 times A1 minus A2. I think you can see clearly what cancels out. I think you can see clearly the M1. You can see clearly the M1 cancels out. So you get here lambda equals G times M1A2 minus M2A1 divide by A1 minus A2. So this is your value of lambda in terms of M1, M2, A2, A1 and in terms of G. Okay, so this is the value of lambda that we can get in this question. Okay, so let's move on to question number 7. An elastic spring has natural length 2a and modulus of elasticity 2 mg. Okay, so let's write everything. You know, it's better to write everything down. So question number 7. What do they say? Natural length of the string is 2a. Modulus of elasticity means the lambda value. Lambda value is 2 mg. A particle of mass m is attached to the midpoint of the spring. Can you see what they are doing? So you have the natural length 2a. So if when you are now the thing is they're attaching a particle to the midpoint of the spring. Remember, whenever they do this, okay, when you attach a particle to the midpoint of your spring, from that point onwards, what's going to happen? Now this is your spring, natural length 2a. So the moment you attach a particle to the middle of your spring, you will be considering this as what? You will be considering this each part of the spring separately. So it's like you will be considering this like two separate springs. The up part you will be considering the forces for that separately, and the down part you'll be considering forces separately. That's how we do this. Okay, right. So they say here, which means what? Which means each part of the spring gets a natural length of how much? If you attach it to the midpoint, I told you you should break it up into two separate parts. Each part will have a natural length of a. Okay, so here the natural length is a, each part of the spring. Because remember, when they attach a particle to the midpoint, immediately you break this into two springs. We are not working with a single spring anymore. Okay. Then they say, okay, so what are they doing now? A particle of mass m is attached to the midpoint of the spring. One end of the spring A is attached to the floor. Okay, one end you are attaching this spring to the floor, and the other one attached to the floor of a room of height 5a. Okay, one end A is attached to the floor of a room of height 5a, and the other end is attached to the ceiling of the room at a point B, vertically above A. Can you picture what's happening here? Okay, so basically you have the ceiling and you have the floor. You have the ceiling and the floor. So the height difference between the ceiling and the floor is how much? The height difference between the ceiling and the floor is 5a. The height difference is 5a. So what are we doing? In the ceiling, you have the point A in the floor, right? One end of the spring, capital A, is attached to the floor. Okay, so at the floor, we have point A. Okay, so you can draw your spring. So this is the spring. I'm drawing it in green. At the top, you have B. The place where the particle is attached to the ceiling is the top point here. Okay, so this is the floor. This is the ceiling, right? Floor and the ceiling height difference is 5A. Okay, now I have a question. I told you now, the thing is, you do realize that the string is extensible. This is an extensible string. There, it's an elastic spring. That's why you are capable of, extending it to a distance of 5A, right? So they are basically this particular part, you take it and you stretch it. Keep it over here and you stretch it to either side. So now, how do you expect this particle to be here? Do you expect this particle to be exactly in the middle of the two springs? Now you know you're keeping it here and you're stretching it, right? Do you expect this particle to stay exactly in the middle of the two springs? Yeah, now you take this system, you take this and you bring it into this room and you attach it. You just take it and you stretch both the sides and you attach it to the floor and the ceiling. My question is, now we did attach it to the middle of the spring. Okay, but the thing is, now you're attaching it to the floor and the ceiling. So what other fact now? Do you expect this particle to now be exactly in the middle?
No, miss.
Thing is, there is weight. Exactly, there is weight. So because of the weight will pull this side down. Now, obviously, if this was kept horizontally, yes, if this was kept horizontally on the floor, to two ends of the floor, yes, it would stay in the middle. Say your A and B was on like this, and you kept it, then definitely the particle would have been exactly in the middle, because then the weight will not make an impact on the spring. But over here, because you keep it vertically, the weight plays a factor. The weight plays a part here, which means what? You cannot expect the particle to be exactly in the middle. Are you with me? You cannot expect the particle to be exactly in the middle. So therefore, what happens? So let's say the exact middle is 2.5A, right? So you will need to expect to see your particle a little bit below the 2.5. It should be a little bit below because of the weight. Okay, now the thing is, let's mark all the forces. Let's mark all the forces. Okay, what are the forces we have? I told you to consider this as two separate springs. So you have the spring at A and you have the spring at B. Are you with me? So what are the forces we have? First thing is, let's mark all the information. We have the natural length of both the springs. So natural length, let's mark it. Complete the diagram. Natural length of the first spring is A. Mark the natural length as well, because we need to mark the natural length. The extensions, we have to mark everything. So natural length is L. On either side, natural length is L. Natural length is L on either side because it's two separate springs. And I told you at the very beginning, natural length of each part will be, sorry, not L. It's going to be L is equal to how much? Natural length is equal to A. Natural length of each individual spring will be A. Natural length of each individual spring will be A. Because I told you the moment you attach this particle, we break this into two springs. We don't work with one spring anymore. So these are two springs. Okay, what else do we need to mark here? So you can mark you have the extensions here, right? You have the extensions. Okay, so before marking the extension, shall we mark all the forces here? What are the forces acting on this particular particle? Okay, so I think you might be having some, I hope your questions, I'm answering your questions right now. So remember the natural length, even though now, again, just to give you a quick overview of what's happening. Remember, you are attaching this particle to the natural length while the spring is at its natural length, not after the spring has stretched. So you are attaching this particle while the spring is at its natural length two way. So the moment you attach it to the midpoint of the spring, remember your spring will immediately we take it as two separate springs. Natural length of the full thing was 2A. When the moment you attach it to the natural length in the middle, it each becomes, the natural length becomes A and A. And then the other important thing is the lambda value, the spring constant. Remember, spring constant is like it's a constant to the spring. So even though the spring divides into two, there's the lambda value divided into two. So lambda is the spring constant. Basically, it gives you an idea about the stretching capability of the string. So therefore, the lambda value is a constant, and regardless, even if you break your spring into two, the lambda value for each part of the spring will remain constant. Okay, so for each part of the string, the lambda value will be 2mg. You don't divide your lambda value by 2, even though you divided the spring into 2 by taking the midpoint, by attaching the particle. Lambda value is a constant. So that is really important. And the other important thing is when you stretch this, now you keep this particle here and you stretch it to either side, right? So when you stretch it to either side, remember the natural lengths are always marked towards the ends, towards the ceiling end and the flow end. You don't mark the natural lengths near the object. Okay, near the objects, you always have the extended ends. Okay, and remember the particle also should be somewhere in between. It does not, while you stretch it from both ends, the particle should be somewhere in between. So naturally, you expect it to be like, as I was explaining the horizontal example. If you took it horizontally and extended to either side, you expect the particle to exactly be in the middle of 5A. So exactly in the middle, 2.5A, 2.5A each. So we try to, but when you do it vertically, so the thing is, even though the particle is in the middle and you expect and you stretch it to either side, you can't expect the particle to exactly be at 2.5A, 2.5A from the center. The reason is because when you're taking it vertically, the weight also plays a part. So when because of the weight, the particle will be slightly displaced from the center. So it will be slightly below the midpoint. It won't be exactly at the midpoint 2.5A, but it will be a little bit below that midpoint. Okay, so I hope this part is clear. This diagram needs to be clearly understood. Okay, natural length natural length A for each part of the spring. I have marked on either end, the ceiling and the flow ends. Okay. Okay, so now we need to. Okay, so now we need to. What are we supposed to find in the question? They are asking us to. They are asking us to find what the spring is modeled as light. Find the distance of the particle below the ceiling when it is in equilibrium. And you can see it's how many marks? It's 8 marks. They've given you 8 marks for this. They're asking you to find the distance of the particle below the ceiling when it is in equilibrium. Okay. So if you try to go with x1 and x2 for the extension, now you do realize any distance the particle is displaced beyond its natural length, we take it as the extension. So you do see there are two extensions here, right? What are they? So we can say this is x1 and this particular length is x2. The length the string has, this particular spring has stretched beyond its natural length. You can see the natural length here. So this is the extension of the spring B. Let's say this is spring B, this part. Let's say this is spring B. Natural length of spring B is A. Extension is this part. Do you see it? And the other one, the spring A. Let's say this is spring A. Natural length is at the end A, and you can see this is the extension of spring A. So my advice at this point is let's not work with x1, x2. It's going to be more tough to you to work with x1, x2. Let's try to work with a single variable here for the extension. So what I'll do here is you do realize that we expected the particle to be in the center and it displays slightly from the center, right? So let's take that distance as x. And what about this distance? Can you all tell me what this distance is? What is this distance? So you can see this is the midpoint, right? So this is the midpoint. The whole length is 2.5A. So from 2.5A, if you subtract this 1A, you do get this distance, isn't it? So 2.5A minus 1A is, this distance is 1.5A. See if this makes sense to you. So guys, you can actually work with x1, x2 if you prefer. Let me just mark the x1 also. What is x1? We can. So I was just trying to make things a little bit easier for you guys. So this is x1. What do I mean by x1? By x1, or let's say xb. xb is the extension of spring B. Are you with me? xb is the extension of spring B. Okay, and then let's go mark XA. What is XA? XA is the extension of spring A. Do you see the spring A? This is the natural length of spring A, right? Now the total length of spring A is this. Do you see that? I'm shading this. Look at this. This is the total length of spring A. Can you see? This particular distance is the total length of spring A. So part of it is made by the natural length. The remaining part is its extension. So this extension part, I've named it as XA. Are you with me? Okay. So this XA distance also you could give in terms of X, because you do realize that this distance is again how much? Because I have taken the middle as 2.5A. You could mark this distance again 2.5A. Do you agree? This is 2.5A. This distance should be 2.5A, right? Okay. So then is it possible for you to tell me this XB, XA distance? Is it possible for you to tell me the XA distance in terms of A and X? This is 2.5A. From 2.5A, what do? You have to subtract the X and the A, isn't it? From the 2.5A distance, if you subtract this X and this A, you can get this XA distance. Are you with me? I'm trying to get this in terms of a single variable. So you can get here XA equals, I hope you guys are with me. 2.5A is this whole distance. From that, I'm reducing this X distance and I'm reducing this A distance. You can see I'm remaining with this small distance, the extension. Can you guys see that? Okay. So XA is equal to 2.5A minus the natural length A minus X. How much is it? XA is 2.5A minus 1A is 1.5A minus X. Are you with me? So XB also value, if you could give me the XB value, the extension of spring B. How much is the extension of spring B? Okay, so this what I have shaded in green is the spring B. So in spring B, this is the natural length is A. So XB is what? XB is this 1.5A plus the X, because it's really important that you know individually the extension of each spring. You must be capable of seeing the individual extension of each spring. Okay, so this is going to be 1.5A plus 6. Agreed, the extension of spring B is 1.5A plus 6. Okay, so let's write here. Tension. So what are the forces acting on this object, by the way? Can I know the forces acting on this object? The tensions and the weights. So there are two springs, so tensions will act on either side. So upward tension, I will mark it as tension B because it's acting on spring B. Downwards, you will have tension B because each spring wants to go to its natural length, right? Each spring wants to go to its natural length. So tension B acts upwards. Tension B will act downwards because it wants to go towards its own natural length. And then this is balanced off by what? What else is there? We have its weight. What was the weight? What was the weight? Weight is, what is the height that they are saying? A particle of mass, simple M is attached to the midpoint. So particle of mass M, which means weight is mg. So now you can make your equilibrium equation. What is the equilibrium equation? The upward tension, tension B, is equal to what? Downward tension is tension A, okay? Downward tension, I'll be using it as, okay, each part of the spring will get its own tension because there are two springs. Each spring should get its own tension because each spring wants to go to its own natural length. That's how we do this. So tension B will be upwards, trying to go towards its own natural length. Tension A will be acting downwards, trying to go towards its own natural length. Okay, so this is tension B, this is tension A. Okay, so tension B upwards equals tension A plus mg. So this is the equilibrium equation. This is the equilibrium equation. Let's apply tension B is what? You know, tension by Hooke's law, tension is always lambda x over L. So this is the place where it's advantages. Now I have got my extensions for spring A and spring B. So tension B is how much? Tension B is lambda. Lambda value we already know. What is lambda? Lambda is 2mg, and you know lambda is a constant that doesn't change. Lambda is 2mg, lambda into extension. XB, let's write XB for now. Lambda x over natural length. What's the natural length of spring B? For tension B comes from spring B, right? So natural length is A, lambda x over A equals tension A. Tension A comes from spring A. Tension A comes from spring A. So lambda is once again, lambda of spring A is also 2mg into extension is XA. Lambda x over L, natural length. What's the natural length of spring A? A. So this is tension B equal tension A plus mg. Okay, guys, so now what can we see? Do you see there's something now in these kinds of equations? If you see something common to every single term, it would be so much easier if you could remove it. So what can I remove from everyone? You can see mg is common to every single term. It's an equation, right? This is an equation. And if a certain term is common to every single equation, that term can be removed because you can take, for example, mg, you can factorize it out and cut it out. It would be easy to remove it. So what's remaining here? 2 times xb over a, 2 times xa over a plus 1. This doesn't become 0, it becomes plus 1. Okay. So now we know our xa and xb values, isn't it? We know the xa value and the xb value. Okay. So here I have used the simple x as the slight displacement from the center. Okay. Do you realize what I have used x as? Okay. So let's use xa, xb values. So 2 times xb value is 1.5a plus x. 1.5a plus x over a equals to twice xa is 1.5a minus x over a plus 1. Are you guys okay with this? Okay, so let's simplify. Can you all get the answer for x? And then, so you can see a is the denominator. Shall I multiply the whole equation by a? So we can cancel out this denominator. So I get here 2 times 1.5a plus x. The a cancels out with what I'm multiplying. Here 2 times 1.5a minus x. The a cancels out. Over here 1 times a is a. From these two sections, the a cancelled out. Open the bracket, make x a subject. 2 times 1.5a is 3a plus 2x. Here 2 times 1.5, 3a minus 2x plus a. I think you can see what cancels out. The plus 3a cancels out. And you get here what? 2x plus 2x, you get 4x. You get 4x equals a. Shall we make x a subject? You need to get x in terms of a. So x is a divided by 4. So this is the distance that the object, that this particle is displacing from the center. As I told you, you expect the particle to be in the center, but because of the weight, it displaced slightly away from the downward from that center. So that slight displacement from that center is 1 over 4a. It's a over 4. A over 4. Now, what are we supposed to do? Is this what we are supposed to do? Is this what we are supposed to find? We are supposed to find what? The question says us to find what? The distance of the particle. Find the distance of the particle below the ceiling when it is in equilibrium. They want you to find the distance of the particle below the ceiling when it's in equilibrium. So this full distance, they want you to find from the ceiling what's the distance the particle is below in the equilibrium position. So this distance, how do you get this distance? It's 2.5a and the x. Can you see, according to my diagram, it's 2.5a plus 6 and we get the distance of the particle below the ceiling. So you can write distance of particle below ceiling. Distance of particle below ceiling is 2.5a plus x. So 2.5a plus a over 4. 0. So let's give it in exact fraction form. This is 5 over 2a plus a over 4. How much is it? So I get here 5 over 2 plus 1 over 4a. I get 11 over 4a. So this is the distance of the particle below the ceiling. Okay, so then in part B, they say in reality the spring may not be light. So the spring may not be light means the spring may have its own mass. That's what they mean. Now in questions, normally what the questions that we deal here, all the questions we work with light springs and light strings. Okay. So here they say in reality the spring may not be light, which means it has its own mass. What effect will the model have had on the calculation of the distance of the particle below the ceiling? They are just asking about the distance. They just wanted to give a comment for 1 mark. You need to give a comment about the distance of the particle below the ceiling if the spring has its own weight. So if the spring has its own weight, what do you think will happen here? Obviously the particle, what do you think? Because of the weight, I mean, now you saw here the due to the weight of the particle, the thing displays from the center downwards, right? So if there is weights of the springs as well, what happens? This will be further displaced down, right? So the distance of the, because the thing will because of the weight of the spring will also will be taken into account downwards. So the particle will be further displaced away downward, will be further displaced down, which means the distance of the particle below the ceiling will increase, right? So the distance of the particle below the ceiling will increase. That's what you have to say here. Okay. Okay, so we'll move on to question number 8. A uniform rod PQ of mass 5 kilogram and length 3 meters has one end P smoothly hinged to a fixed point. Okay. The other end Q is attached to one end of a light elastic string of modulus of elasticity 30 Newton. So can you see what's happening? You have a uniform rod PQ, one end of the rod is hinged. Hinge means like it's free to rotate around that end. So around the end P, your rod is free to rotate. And then how do you keep this in equilibrium? They say to the other end Q, they're attaching a light elastic string. A light elastic string means a string that can stretch. Okay, so then they have attached a light elastic string at the other end of modulus of elasticity 30 newtons. The other end of the string is attached to a fixed point R, which is on the same horizontal level as P, with RP equal 5 meters. The system is in equilibrium with angle PQR equal 90 degree. Okay, they're asking you to find the tension. Okay, before you do any of the other stuff, the most important thing here is to read this information and actually draw the diagram. Okay, so the first thing you need to realize here is, now they say the first end of the rod is P, right? So from the end P, if you hinge the rod, do you expect the rod to just, stay just horizontally like this? Can you expect the rod to stay up like this? No. So if you just hinge it, yeah, the rod will, just stay down. It's hinged at the end P. It's hinged at the end P, right? It's smoothly hinged at the end P. So what they do here is in order to create this angle, okay, they are attaching the other end of the, rod to the elastic string. Okay, so let's say, so you need to kind of like see how the diagram works. So this is the rod. Okay, so it will be in an inclined angle like this, right? It should be in an inclined angle like this. So this end is hinged. This is hinged. This is end P. So how does it stay in this manner? We are attaching this to what? They say the other end Q is attached to the elastic string. The other end Q is attached to an elastic string of modulus of elasticity 30 Newton. And the other end of the string is attached to a fixed point R. The other end, now you're attaching a string here, right? So you're attaching a string here and they're saying the other end of the string is at the point R, which is in the same horizontal level as P. So now you can see the horizontal level of P, right? The level that you hinged. So this is the horizontal level P. They are saying that they are attaching one end of the light elastic string to end Q, and the other end of the string is somewhere at a point called R, such that P and R are on the same horizontal level. Can you see? And they say PQR, PQR should make a 90 degree, which means over here we need to create a 90 degree. So draw this string in such a way you create a 90-degree here. Can you see that I have created a 90-degree? So over here it's a perpendicular and this is the point R. So guys, now it's time to mark all the forces. Shall we mark all the forces? It's a uniform rod PQ of mass 5 kilogram means a uniform rod means what? The weight acts at the center. So you mark the weight at the center, 5 kilograms. So this is 5G. Okay. And what else do we have? So you have a uniform rod of mass 5 kilograms. I mark the weight at the center. P smoothly hinged to a fixed point. Okay, so this uniform rod is smoothly hinged. You do need to remember when it's hinged, you need to remember you need to mark two normal reactions. Whenever they say that the rod is hinged, even in M2, you need to remember that you mark two normal reactions, and these two normal reactions, you can mark it to any two directions as long as the two normal reactions are what? As long as two normal reactions are perpendicular to each other. So I will mark the two normal reactions since I can see the weights and everything coming vertically. I will mark the two normal reactions vertically and horizontally. So I will mark the first normal reaction upwards like this, normal reaction Y, and I will mark the other normal reaction. Either I could mark it horizontally to the left side or to the right side. So you can just think and mark because I can see the tension is pulling this to the left side in order for the system to be in equilibrium. I can kind of like see this normal reaction. X should be to the right side, should be to the left side because I can see this tension over here will pull this to the right side. So you can kind of guess that even if you mark this in the wrong direction, you would just get the answer as negative, which tells you the direction that you use has to change. Okay, in an event if you mark it wrong, these two directions, because we speculate and mark these two directions. Okay, so definitely RY, you need to realize normal, you have to definitely mark two normal reactions here. I understand because of all the weight components, one normal reaction should definitely act upward to counter effect the weight. And here I can see this tension is kind of, you have a tension in this elastic string, right? In the elastic string, you have a tension at this point. So this tension will give you a component to the right side. So to balance off, because the system is in equilibrium, they do mention the system is in equilibrium. So you need to kind of like, you can think and see, okay, the other reaction force, we could mark it to the left to counteract this. So these are the ways that you think and mark the forces. It's essentially important that you mark the two normal reactions here. Okay, so two normal reactions can be in any two directions as long as they are perpendicular. Even you could mark normal reaction Y in this way and normal reaction X like this. Like you can see, I've given the two perpendicular directions. So just go with one direction that is the easiest for you. So I have taken horizontal and vertical as the easiest at this point. Okay, so I have marked the weight, I have marked the normal reactions, I have marked the tension. Okay. Okay, so after marking all the forces, actually at the end over here at this particular end, you have another tension because the string is attached to the to this point R. You could mark a tension over here, but remember here our focus is on what? Our focus is on the rod. The rod is what is the focus here. So you really don't need to mark this tension here because we have actually marked all the forces acting on the rod. This tension acts on the rod, the weight acts on the rod, the reactions, the normal reactions are also acting on the rod. Basically, the whole force diagram here is concerned and it's centered around the rod. So this tension is not required because we are marking all the forces acting on the rod. Okay. The next thing we can do is you need to realize to take now. Obviously, we are going to go with either taking moments. If the system is in equilibrium, we need to either consider moments or we need to either consider what? The equilibrium, vertical equilibrium and horizontal equilibrium. That's what we have to do here. So to do that, you need to realize we need an angle. We need an angle. Okay, so there's a 90 degree here. Shall I mark this angle as a theta? Let's mark this angle as theta. And is there any possible way for me to get this theta value? So have they given us any length? So you can see here they have given you the length, a uniform rod PQ of mass 5 kilogram and length 3 meters. So they have told you this PQ length is 3 meters. And what else? They have told you the other thing over here, RP. RP length is 5 meters. Mark it clearly on your diagram. So you can see that this is originally a right angle triangle, isn't it? This is originally a right angle triangle, which means I can also get the length of what? This is a right angle triangle because the question says PQ bar is 90 degrees. So if there's a 90 here, R cube length will be, you can find the length of R cube by using what? By using the Pythagoras theorem. So by using Pythagoras theorem, the hypotenuse, you can see here, this 5 meter is the hypotenuse. Can you see? So the other two lengths, you can apply Pythagoras theorem. 5 square equals 3 square plus x square. What do I get here? 25 minus 9 equal x square. So 25 minus 9 is 16. Root 16 is x, which means the RQ length is 4. So this distance is 4 meters. This distance is 4 meters. Is that okay? This distance is 4 meters. Okay, so now the question says you to find the tension on the tension in the string. Okay, how do we find the tension in the string? Okay, so we have to find the tension in the string. Basically, we have to find the T value. Okay, and in part B, they want you to find the natural length of the string. Okay, so I had to find the T value. So you need to realize, is it possible to find the tension by using T equal lambda x over L? Because you might be tempted in thinking, okay, can't I find the tension using lambda x over L? But you can see to find tension using lambda x over L, though the lambda value is given, modulus of velocity lambda is given. Do we know the extension? Do we know the natural length? No, we know the full length. We know the natural length plus the extension. So your natural length might be this. Extension and natural length. We know the natural length plus the extension. But we don't know each of these two values individually. So tension lambda x over L, you cannot use it in part A. So to do part A, you will have to use some of the tricks you have learned in M1 and M2. So basically what to find tension, we can consider either moments or we can go with vertical equilibrium or horizontal equilibrium. So what is the most advantageous thing to use here? I want to find tension. And you can see right now tension is an unknown. And you can see here normal reaction Y, normal reaction X are also unknown. There are 3 unknowns. So the easiest way to get rid of, you have to get the T value. So to find T alone, it's best to consider what? Moments around P. If you take moments around P, Ry, Rx both of them will not make an effect on the sum. So we will take moments around P. Okay, let's take moments around P. Okay, let's start taking moments. So moment is force into perpendicular distance. Moment is force into its perpendicular distance. So you have to get the force into its perpendicular distance. First one, I'm taking moments around P. And let's consider the force T. So when you consider force T, do we know the perpendicular distance from force T to point P? I think you can see from force T, the perpendicular distance from force T to this point P is directly 3 meters because it's directly a perpendicular distance. Can you guys see what I'm talking about? Force T, the line of action of force T goes like this. The perpendicular distance from the place that you're considering moment to this T is directly 3 meters. So the moment here is T into 3. Is it a clockwise moment or anti-clockwise moment? So keeping keeping the point around P. So you can see here, this is pulling which way? So I can show it to you from this. Okay, so you keep this force here. So you can see when you pull it along the direction of P. When you pull it along the direction of P, you can see it's pulling which way? What kind of a moment are we creating? We are creating an anti-clockwise moment. Is that clear? So it's an anti-clockwise moment. This is anti-clockwise. Let me say, so you can choose a positive direction. Shall I choose clockwise as positive? If I choose clockwise as positive, T into 3 will be an anti-clockwise moment. Therefore, it will be negative. Okay. Okay, so now let's take, I have taken moments with the force T. Now let's take moments with The other force to consider here is 5G. Okay, so the other force that you need to consider here is 5G. So when you take 5G, okay, so one thing you could do here is either you could resolve 5G into two parts, or you could simply take the line of action of 5G and consider the perpendicular distance from the force 5G to point P. So at this point, you can see P to this force 5G, you have this slant distance. So I don't want the slant distance. I want the direct perpendicular distance. How do I get the direct perpendicular distance? You need to take this force, extend the force along its line of action. This is called the line of action of the force. So this is the line of action of the force. Are you guys with me? So you need to consider the perpendicular distance from the line of action of the force. So this is the perpendicular distance. Do you see this distance that I'm marking in red? This red color distance that I'm marking over here, this is the perpendicular distance from point P to the line of action of 5G. I hope you guys can see this. So your task is now to find the perpendicular distance that from P to this particular line, to this dotted line. So how do I get this distance? What do we know about the length here? You know this object, the 5G acts at exactly, it's a uniform rod. So the weight 5G acts exactly in the center of PQ, right? Which means this distance from P to the P to the 5G is 1.5 meters. Guys, do you agree? This is 1.5 meters. So this is the hypotenuse of this particular triangle. You could resolve 1.5 and you can get the red color distance as what? This red distance can be 1.5 cos theta. Guys, do you agree? This distance can be 1.5 cos theta towards the angle. Okay, so now I have the perpendicular distance from the between the force 5G and the point P. Okay. Okay, so then the other force is 5G into 1.5 cos theta is the distance. So weight 5G into 1.5 cos theta. Now the question is this a positive moment or a negative moment? I have used clockwise as positive. So if you consider here the 1.5G, sorry, the 5G, is the 5G giving a clockwise moment or anti-clockwise moment? As you can see, the 5G, the arrow is pulling downwards. Can you see the arrow is pulling downwards, which means this I should consider this downwards because the arrow pulls it down. Can you see which way is it moving? It's moving clockwise, which means this is positive. It's a positive moment. Okay, so then since are there any other forces who gives me any moment around the point P? No, which means what? Which means this system is completely in, I mean, because the system is in equilibrium, the sum of moments, there are no other forces to give me moments, which means the sum of moments must be 0 because moment is the turning force. Rx and Ry will not give any moment because you consider moments from point P and Rx, Ry both pass through point P. So there is no perpendicular distance. The force, when it passes through the point that you're considering moment, that particular force will not give you a moment, M1. Okay, because Rx, Ry both pass through point P, which is the place that I'm considering moment. That is the whole reason why I took point P to take the moment. Because then Rx, Ry will not make any effect. That is the reason I chose point P. Now what you have to do? Make P the subject and immediately you have the tension. So let's get the answer here. What do we get? 5G into 1.5 cos theta equals 3T. Guys, do I know the cos theta value? Is it possible for me to get the cos theta value here? You do realize I have a right angle triangle. Cos theta is adjacent over hypotenuse. Who is the adjacent for this theta? 5G into 1.5 cos theta adjacent over hypotenuse. This is theta. This 4 meter is the opposite. So this 3 will be the adjacent and hypotenuse is 5. Cos theta is adjacent over hypotenuse. Simple trigonometry in O-level maths. Cos theta is adjacent over here and hypotenuse is right opposite of the 90 degree. Equals 3T. Okay, so you can get your answer and also you need to remember whenever you use G as 9.8, do you remember? Whenever you use G as 9.8 to do a sum, you must leave your answer to 2SF or 3SF. You do not keep it to more significance than that. Okay, because that's the instruction that they ask you to follow in the exam, isn't it? Okay, so let's get the answer here. I think I can cancel out the 3T, 3 and 3. Can you see? Because the 3 anyway goes down as a division, right? So I can get here T equals 5 into G is 9.8 into 1.5 divided by 5. How much is T? Exactly 14.7 to 3 S. So it's already to 3 S. 14.7. Tension is 14.7. Or you can give the answer in terms of G also. If you want, you could have given your answer in terms of G. Okay. Okay, guys, so let's move to part B. They ask you to find the natural length of the string. How do I get the natural length of the string? So you can see here 4 meter is the complete length. Okay, natural length is simply this, the L value that I want to find. So we can, since we know the tension now, I can use tension equals lambda x over L. So now I can use it. Previously, I could not use it because I did not know most of the values, but now tension value I know. Tension value we got it as 14.7, isn't it? We just got the tension value as 14.7. Lambda value was given in the question as 30. Lambda value is given in the question as 30. Extension. So actually you can see here the extension is this particular distance, right? So the thing is, yeah, let's give it in terms of L because I want to find L. 4 minus L. 4 is the whole distance. 4 is the complete distance here. So it's better to give our x in terms of L. So L will be, x will be 4 minus L over L. So 14.7 L, 30 times 4 is 120 minus 30. I'll take all the L terms to one side. 14.7 L plus 30 L equals 120. How much is 14.7 plus 30 L? That is 44.7 L. 120 over 44.7. So I think you get quite a large answer, right? Yeah, so you can give it to, I think you get an answer here 2.684563. You get a really long answer, but you must keep your answer to 2 or 3SF, either 2SF or 3SF, because once again we have used this the G value here. The G value which we use here is used over here. So do not write long answers. 2SF would be better because this is already to 3SF. If this is the 3SF, you can make it to 2SF, 2.7 meters. Okay, is this clear? Okay. Okay, so next we'll move on to question number 11. Okay, a particle of mass 2 kilogram is attached to one end P of a light elastic string PQ of modulus of elasticity 20. Lambda is 20. You're attaching a mass of 2 kilograms and natural length 0.8. L is 0.8 meters. Okay. The end cube of the string is attached to a point on a rough plane. Okay, what do we have? So at the end P, now they are saying there's a particle of mass 2 kilogram attached to one end of a light elastic string. Okay, so you have this light elastic string. One end of the light elastic string, you're attaching the particle P. And they say the other end of the string is the other end Q. This other end Q of your string, you're attaching it to a point on a rough plane, which is inclined at an angle alpha to the horizontal, where tan alpha is 3/4. So basically you take this string and you keep it on an inclined plane, on a rough inclined plane, basically. So you go to a rough inclined plane. Let's draw a rough inclined plane. And what do? How do you expect this particle to be? Can you mark the particle at the top and point Q at the bottom? Definitely no, right? You need to realize according to the slope of the thing, the Q, the place where you're attaching Q should be at the top. Okay, and the particle should be at the bottom, right? So along the plane. So then with the weight of the particle, there will be some kind of extension as well, right? You know that when you keep it because of the weight, there will be some extension. So then you draw it like this. Can you see? So this is my particle. So this is particle Q, particle P, and this is the end Q. Are you guys with me? So natural length of the object is, so mark it. Always natural length, you mark it not at the end of the object, but at the other end. Okay, so at the object end, and near the object, it's always the extension. So over here, I will mark the natural length, 0.8 meters, natural length. This is the L. Are you with me? So over here, this should be your extension. This should be your extension. Can you see the diagram? It needs to be really good. The diagram should be quite clear to understand what's really going on. And also you have the slope here, right? The angle is alpha, and they have told you tan alpha is 3/4. So if tan alpha is given as 3/4, what can we immediately do? We can find the value of cos alpha and sin alpha by using the triangle. Let's draw the small triangle, a right angle triangle, and actually get sin alpha and cos alpha. So tan alpha is opposite over adjacent. Tan alpha is opposite over adjacent. How much is the hypotenuse? By considering the right angle triangle, 3, 4, this should be 3 square plus 4 square square root. So 9 plus 16 root is root 25, which is 5. Guys, do you agree? Okay. Cos alpha will be adjacent over hypotenuse, right? So adjacent according to this triangle is 4/5. Sin alpha is opposite over hypotenuse, 3/5. So I have my cos alpha, sin alpha, everything ready. Now what do we need to do? Let's read the remaining part. The coefficient of friction between the particle and the plane is half. Okay, they have told you that this is a what plane? It's a rough plane. So rough plane means you have friction working here. Okay, what else? They say the mu value. Okay, in the question, they say the mu value is half. The particle rests in limiting equilibrium. Okay, the particle rests in limiting equilibrium on the point of sliding down the plane. So it's on the point of sliding down the plane. Okay, with P cube along a line of greater slope, find the tension in the string. Okay, so there are several things to consider here. The first one, it's in limiting equilibrium and it's on the point of sliding down the plane. Why do they give you this on the point of sliding down the plane? If you remember M1, why do they give you on the point of sliding down the plane? This is given to you to identify the direction of friction. Because friction, it always tries to, it opposes the direction that you're trying to move. So if it's on the point of sliding down the plane, friction is trying to oppose that. It's on the point of going down the plane means your friction will be acting upwards. So friction force, and that's also because it's in limiting equilibrium, you have what friction? You have the maximum friction, which means the mu r friction. Limiting equilibrium means you have the maximum friction, the mu r friction. Okay, right. So what are the forces do we have here? So you can do this from your M1 knowledge. You have the weight. Weight is 2 kilograms. Mark the weight. Weight 2 kilograms. So 2g. What else? You have the normal reaction acting perpendicular to the plane. Okay. And what else? You have the friction, you have the weight. So actually, when you do remember in M1, when you have working in an inclined plane, we have the habit of what? Taking all our forces in the direction along the plane and perpendicular to the plane. So you can see here friction is along the plane, normal reaction is perpendicular to the plane. I need to fix the weight component. Shall we fix the weight component? So how does the weight component work? How does the weight component, how does it resolve? So you will get here. What are the weight components? Do you remember M1? So this alpha comes over here, right? This alpha in M1, you have done this. This the geometry, this alpha comes over here. So this component will be 2g cos alpha, and the one along the plane is gonna be 2g sin alpha. So these are all the forces acting on particle P. And what else I have? There's one more to mark, right? With the string, there is a tension. With this elastic string, you'll have tension. Agreed? So you have tension. Okay, so these are all the forces acting on the plane. The particle is in equilibrium. So if the particle is in equilibrium, you know there are two major directions here. The first direction is along the plane. The other direction is perpendicular to the plane. So these are the two major directions that we use for x and y. So along the perpendicular direction, the forces must be balanced, and along the perpendicular direction also forces must be balanced, which means what do you get here? Perpendicular direction, what do you get? If you consider equilibrium along the perpendicular direction, what do you get? R is equal to 2g cos alpha. R is equal to 2g cos alpha. Okay, so cos alpha value, since we know it, shall we input it? Cos alpha is 4/5. Cos alpha is 4/5, which means R will be equal to 8g/5. Okay, then shall we consider equilibrium along the plane? Along the plane, what do we have? Tension upwards, and F max plus the friction. F max, not just friction, but the maximum friction, because it's in limiting equilibrium. F max, tension plus F max upwards must balance out with 2g sine alpha. So tension plus what about F max? F max, we are supposed to find tension. I want to make tension the subject. Who is F max? F max is mu r equals 2g sine alpha. Let's input the value sine alpha 3/5. Shall we find the tension in terms of g? So when you have g, it's better to get the answer in terms of g. Otherwise, when you use g as 9.8, you'll give your answer 2SF or 3SF. Okay, so let's give it in terms of g. Mu is given to us. In the question, mu is given as half. Normal reaction we just found. Here, normal reaction we just found. It is 8g/5 equals 2g into 3/5. Agreed? So I get here tension plus half into 8g is 4g/5 equals 2g into 3/5 is 6g/5. So I get here tension equals 6g/5 minus 2g/5, which gives me, sorry, tension 6g/5 minus 4g/5. I'm sorry. So tension is 2g/5 newtons. Is that okay? Yeah. We can give it as in terms of g. Better to give tension in terms of g. Okay, so part B, they want you to find the length of the string. How do you get the length of the string? So how do you get the length of the string? The length of the string, in the sense they want the complete length of the string, natural length plus the extension. That's what they want. How do you get that? We got the tension. So the tension value I gave in terms of G. By the way, this tension value, if you use G as 9.8, just give it to 3SF or 2SF. Okay. So anyway, when you're going to part B, try to use the full value. Okay. If by any chance you use a decimal figure here to 2SF, you keep the final answer. In part B, since I will be using the tension to get the natural length, the thing is use the full value in that case. Okay. So anyway, I will be using the full value here. Tension equals lambda x over L. Tension is 2g/5. Lambda was given to us in the question. Lambda is 20. Lambda is 20. Extension is unknown. Natural length 0.8. Natural length is 0.8. Make x the subject. 2g into 0.8 over 5 times 20 equals x. So now you will type 2 times 9.8 times 0.8 divided by 5 times 20. Can I know the answer? The x answer you can type in the cal. 2 into g is 9.8 into 0.8 over 5 times 20. X is 0.152. You can take it to more SF. Anyway, this is not the final answer. Remember, whenever you use G as 9.8, answers are either 2SF or 3SF. Okay, this is not the final answer. Final answer is the length of the string. So length of string is x plus L. X is 0.1528 plus natural length L is 0.8. So add everything and give me the answer to 2SF. 0.956, so basically 0.96. Make sure you give the answer to 2SF or 3SF. So over here we'll keep it to 2SF. Okay, why do we keep it to 2SF? Whenever you use G as 9.8, you must keep the final answers to 2SF or 3SF. So 2SF. I kept it to 2SF. Okay, so there is a request to do question number 10 as well. Shall we do question number 10 quickly? Okay, so they say here, an elastic string PA has natural length 0.5 meter and modulus of elasticity 9.8 Newton. The string PB is inextensible. Okay, so this is really important. So you have an elastic string PA and the other string is inextensible. Remember, inextensible means the normal strings that you use in M2 and M1, which means there is no extension, just the normal string. The end A of the elastic string and end B of the inextensible string are attached to two fixed points which are on the same horizontal level. So let's draw the diagram. There you have the same horizontal level. So there is this one horizontal level. The ends of the strings are on this same horizontal level. Okay. The ends A and B. So shall I just mark end A one over here, end B the other one over here? End A and B are on the same horizontal level. And what do they say? So I think you have the two strings meeting down here, right? P. Okay, the end A of the elastic string and end B of the inextensible string are attached to two fixed points which are on the same horizontal level. The end P of each string is attached to a 2 kilogram particle. So end P is attached to a 2 kilogram particle at the bottom. So before I draw it at the bottom, let's see how the angles have they specified about the angles. The end P of each string is attached to a 2 kilogram particle. Okay. The particle hangs in equilibrium below AB, obviously, with the weight usually below AB, with PA making an angle of 30 degree with AB and PA perpendicular to PB. Do you see what's happening here? This point P, PA and PB are perpendicular and they say the angle that you make here is 30 degrees. So let's draw it. There's a 30 degree angle over here, the string. This is the 30 degree string. So over here you have your particle of mass 2 kilogram. And the other side you have the other string. Can you see they say PA and PB are perpendicular. So this is P, PA, PB are perpendicular, which means you have a right angle at this corner. Is this clear? Okay, so then the weight of the particle is 2 kilograms. The weight of the particle is how much? 2 kilograms. It's attached to 2 kilograms. So weight is 2G. Okay, so now you need to keep in mind the PA string is elastic, the PB string is inextensible. Okay, right. So which means the PA string has a natural length. The PA string has a natural length and it has an extension. Got it? The other string does not have any of that. Okay, so what do they want you to do? They ask you find the length of PA. Okay, they ask you to find the length of PA. Find the length of PA, then they want you to find the length of PB and they want you to find the tension in PB afterwards. Okay. First, shall we mark all the forces? What are the forces we have over here? There are two strings. Each string must have its own tension. So shall we mark the tensions? We have tension. I'll mark this tension A to the end A. And this one I'll mark it as tension B. So remember tension A, you get it from the elastic string. So for tension A, we can apply what law? For tension A, we can apply Hooke's law. Can I apply Hooke's law for tension B? No. Okay, we cannot apply Hooke's law for tension B. That's really important. You should not use tension B as lambda XOL. Okay, right. So they're asking me to get the length of PA. Okay, so how do we do this? The length of PA in the sense, I think you need to realize they're asking me to, I want the length of the natural length and I want the extension, right? Okay, so have they given us any of the length? Yeah, they have told me that in elastic string PA has natural length 0.5 5. Okay, as you can see, natural length is given. Natural length is 0.5. So this is given to you. Natural length is given to you. Do you agree with me? Okay, so the only thing to do here is to find the extension. They want you to find the length of PA. However, to get the PA length, okay, what do I need to know? I need to know the tension of A. I need to know the tension of A. Then I can use tension A is lambda x over L, and I can find the value of x. How do I get the tension of A? And you can see in part B they want in part C they want the tension in PB. So you need to realize one thing here. What is it? Can we find tension B in the process of finding tension A? Can we find tension B in the process of finding tension A? No. Why? You can see they want the tension TB in which part? In part C. So you know the rule. You cannot use part B, C answers to do part A. That will be completely wrong. So you need to find a way to find tension A without involving tension B. So if you try to do this in the typical way, what's the typical way that we normally do? We try to go for equilibrium along we go for horizontal equilibrium and vertical equilibrium, right? So this is 30 degrees. You can take the 30 degrees over here and you can, and this is 60 degree, right? Because this is 30, this is 90, this should be 60, which means over here you will get a 60 degree. Do you agree with me? So you can see if you go for the typical equilibrium, you have tension A cos 30 equal tension B cos 60. Can you see? And the other side, you get tension A sine 30 and plus tension B sine 60 equals 2G. So do you see that if you do in that particular manner, you will end up creating two simultaneous equations with TA, TB. And that helps you to find TB in part A itself. Are you with me? So you need to do this in such a way where you don't involve TB at all. How do I do this in such a way where I don't involve the tension B at all? Because tension B is specifically required only in part C. So how do we do this in such a way where tension B is not involved at all? Okay, so what I'll do here is, children, now you don't, the thing is, when you're resolving forces, always the resolving should be in two perpendicular directions, right? But it doesn't necessarily have to be always the horizontal, the typical horizontal and the typical vertical. As long as you resolve in two perpendicular directions, we should be good. It doesn't need to be always the typical vertical and horizontal. So look at what I'm doing. So what I'll be doing here is I'll be erasing this and I'll be resolving. Okay, I'll be resolving using these two perpendicular directions. Look at this. I'm going to resolve by using, look at the directions that I'm using. Let me okay, look at this. I'm going to resolve in these two directions. Now, are these two directions perpendicular to each other? Are these two directions perpendicular to each other? Yes, you can clearly see there's a 90 degree in between them, right? So as long as you resolve in two perpendicular directions, you should be good. So now in this case, if you resolve to these two directions, do you need to do any change to tension A and tension B? No, tension A and tension B are in the specific directions. The only person I had to resolve here is the 2G. The only person I had to resolve here is the 2G. Shall we try to get the angle here? So what is the angle I need to consider here? What is the angle I need? Because I need the angle to resolve the 2G. So how do I get the angle that I require? I think you can see here if it's a 30 degree. Okay, so they are considering, I just drew the line here. This should be 90, which means this angle should be 60, right? And I think you can see this straight line comes here and you have this. So you can see that this angle will be 60. Do you agree with me? Vertically opposite angles. Can you see vertically opposite angles here, guys? Do you see vertically opposite angles here? So this 60 comes over here. Can you see how I got 60? This is 30. This over here when I drew this line to the top. This is the 90 degree because it's a vertical. This is a horizontal. So this will be 90. So therefore, this should be 60. That's 60. You can take it over here as vertically opposite. Now, can't we resolve the 2G? So how does 2G resolve? Towards the angle, this resolves as? Yeah, towards the angle, you can resolve this as what? 2G cos 60. The other way, you resolve this as what? 2G sin 60. 2G sin 60. Guys, do you get what I'm doing? This is 2G cos 60 towards the angle. This is 2G sin 60. So now do I need to work with this 2G now? No, so now I have resolved. And now you can see we can consider working with these two directions instead of the typical direction. Because I have completed my resolving in perpendicular direction. So tension A and tension B, I don't need to do any change to it because it's already in the specified directions. I don't need to change anything over there. So what can I say from here? In part A, to get the length of PA, what can we say? Tension A is directly in balance with what? Tension A is directly in balance with 2G cos 60. Tension A is directly equal to 2G cos 60. Okay? And tension B is directly equal to 2G sin 60. But that we will not write, that we will write in part C. So you can see now I can get tension A without any interference from tension B. Okay, so tension A, can I have the value? 2 times G is 9.8, cos 60 is? Cos 60 is half, right? So tension A is simply 9.8 or just the G? Just the G, 9.8. Okay, so then let's use part B. They want, part A, they want me to find the length of PA. So what's the length of PA? Tension A is the elastic string, lambda x over L. So tension A is 9.8. What is the lambda value? The lambda value is, guys, how much is the modulus of velocity? Can you see the modulus of velocity? Lambda is 9.8 into x value. The extension is x. Natural length is 0.5. So what do you get here? 9.8 into 0.5 divide by 9.8 equal x. So what do you get here? 9.8, 9.8 cancels out and you get x equals 0.5. X equals 0.5. Do you agree with me? So then what's the length of PA? What is the PA length? So PA length is natural length plus the extension. So what is the PA? PA length. So PA length will be natural length plus extension. Natural length is 0.5 plus extension is 0.5. I end up getting 1 meter. PA length is equal to 1 meter. Okay, part B. They want you to find the length of PB. So guys, to get the length of PB, is it possible to use again the equation tension is lambda x over L? So what did I tell you? Tension B, the string B is inextensible, which means there is no, you cannot use tension is lambda x over L. Hooke's law does not work for inelastic strings. These are inextensible strings. So this doesn't work. So how do I get the length of PB? So the easiest way to get the length of PB here is to what? Simply just look at this as a what triangle? This is a right angle triangle. Isn't it? This is the right angle triangle. This is APB. You want to get the PB length. We already found the AP length. What is the AP length? The AP length is 1 meter, right? The PA length, you got PA length as 1 meter, isn't it? So PA length is 1 meter and you know that this angle over here is 30 degrees. So can't you easily get the length of PB by using simple trigonometry? Sine, cos, tan. Which ratio should I use? So for this 30 degree, this is the opposite side. This is the hypotenuse and this is the adjacent. So I could simply go with cos 30. We can't go for resolving. By the way, you don't try to resolve 1 meter because 1 meter is not a hypotenuse. Only hypotenuse can be resolved towards the origin and towards the angle and away from the angle. Over here, the 1 meter, you shouldn't resolve this as 1 cos 30 and 1 sin 30. That will be wrong. Okay. So only hypotenuse can be resolved. So this will be, I can go with cos, sorry, I can go with tan, right? tan 30 is the opposite over adjacent. Tan 30, tan theta is opposite over adjacent. So opposite is PB over adjacent is 1 meter. So PB equals 1 times tan 30. So 1 times tan 30 is tan 30. How much is tan 30? Tan 30 is simply root 3 over 3, right? In the cal, it rationalizes and gives. Tan 30 is root 3 over 3 in the cal. Am I correct? Yeah. So do they want it? You can give the decimal figure here as well, or you could give it the answer. What is the answer to 2SF? Root 3 over 3? 0.58 meters. So this is the answer correct to 2SF. Okay, let's go to the last part. Part C, the tension in PB. So tension in PB, is it it's something that's really simple now because of our special the way that we resolved. Tension B is immediately gonna be 2G sine 60. So input the value and get me the tension B. How much is it? 2G sine 60 is root 3 over 2, which means I get tension B is root 3G, exact answer. If you give it in decimals, so with G value 9.8, you can give your answer 3SF or 2SF. What's the 2SF answer? Yes, 17 point, how does it go? 16.974, 16.974, correct to 2SF, 17 newtons, and you just make sure you write. Now, when you are making it to significant figures, just mention that you have written into that significance. Okay, mention the significance that you have given in the answer. So over here, I wrote 17 newton to 2SF. Okay, so this is the, these are the answers for question number 10.